Let's summarize now some of the highlights from week 6. We started off doing a number of videos on space-time diagrams revisited, and this is sort of where we ended up, one of our final diagrams. In other words, the idea was we wanted to combine both frames of reference into one diagram, so both Bob and Alice, where, as usual, we had Bob traveling at velocity v, although I guess sometimes we've had Alice doing that as well, but Bob traveling at velocity v to the right, Alice observing. Here was the Lorentz transformation. If we were given coordinates in Bob's frame of reference, we can transform them, of course, into Alice's frame of reference, into her coordinate system. And we want to figure out how to plot that and see them on the same plot, or really two plots in one. And by using the Lorentz transformation and starting with Alice's normal plot, right angle plot, we're able to get Bob's axes on there as well. So, of course, we have Alice's x-axis and t-axis. And with respect to that, then, Bob's x-axis is at an angle, and his t-axis is also at an angle there. And the angle depends actually on the relative velocity between the frames, because that gives us the slope of those lines. And we also noted that, of course, we have lines of simultaneity and lines of same location. So for Alice, the lines of same location are just the straight vertical lines. In other words, 1, 2, 3, 4. If I've got 4 right here for Alice, everything that occurs on this vertical line is at the same location, going through time. So if something is just sitting there, we've talked about this before, even before this week, if something is sitting in Alice's frame at position 4, its world line is just going to be a straight vertical line there. And for a horizontal line for Alice, the world line there just indicates something or a series of things that are all simultaneous in line with each other there. And of course, you can just step through time that way. For Bob on this plot, however, because the axes are skewed, remember we have to draw the lines of simultaneity parallel to the time axis, and the lines of, actually I said that backwards here, lines of same location parallel, now which way I said it now, so I'll say it correctly this time, lines of same location parallel to the time axis, lines of simultaneity parallel to the x-axis there. So you get this skewing effect. But for a given space-time event represented by this, say, a flash of light or whatever, this red dot here, we can, it's the same event, but Bob and Alice will just have different coordinates for that. And so in this example here, we can see that flash of light for Bob occurs, say, at x sub b equals 1, and t sub b equals 1, 2, 3. Those are the coordinates for Bob. X equals 1, t equals 3. For Alice, those coordinates, though, same space-time event, roughly speaking, it's not an exact diagram here, but I've got it about 2.5 for x there, and 1, 2, 3, maybe 3.5, maybe a little bit more for the t coordinate there. So Alice and Bob, same space-time event, but they read it in different coordinates, or observe it with different coordinates. We also noted that you can see time dilation on here, because note that for this event, Alice is reading it at, again, time about 3.5, something like that. For Bob, the time is 3. Alice, again, observing Bob's clock, would be observing it running slow, time dilation. And same thing for length contraction here, that if you look at the distance for Bob here, it's at x sub b equals 1. Alice is reading it at x sub a equals 2.5 or something like that. So as she observes Bob going by, remember that's the basic picture here. She is observing Bob going by at some velocity v. She sees objects in his frame of reference contract their length versus their rest length in Bob's frame of reference. So you can see both length contraction and time dilation if you look at the diagram carefully here. You can also see, remember, the relativity of simultaneity, because we did an example where Alice had a whole series of flashes that went off simultaneously. So that would be on one of her lines of simultaneity here. So let's just do it on this one here. So a flash there, and get a few more in here, roughly speaking. They're a little off. But okay, those are all on a horizontal line in Alice's diagram here, meaning that to her they're all simultaneous. They all occurred at t equals 1. So it's like having a line of flash bulbs that for Alice they all go off at the same time. They're all synchronized with her synchronized clocks. And so if you were to take flash photographs of every flash there compared to the clocks at the location, all Alice's clocks would read the same time for those flashes. But look what happens in terms of Bob here that we can see. Now, of course, we know from the Lorentz transformation there's going to be a difference, but we can see this right off the diagram because Bob's lines of simultaneity are, like this. Okay, so he sees, let's actually just try to draw this in here a little bit. So his line of simultaneity, one of them looks like that. Another one right here. And sort of crooked there, but hopefully you get the idea. So all these are synchronized and simultaneous for Alice, but clearly for Bob, if you look at, let's just pick some in the middle here. This one right here occurs between time t equals 0 and 1. This one over here, though, is occurring after time t equals 1, this line of simultaneity. And this one way over here occurs after time t equals 2. So in other words, to Bob, these flashes are occurring before these flashes. In fact, you will see it go off as flash, and then flash, and then flash, and then flash. There will be a series of flashes, not simultaneous, but in line with each other. And again, also, you may remember, we can see leading clocks lag on this as well, because to Bob, these clocks or flashes are moving to the left, because to Alice, he's moving to the right. And it's this flash over here, the leading flash, the leading clock, as it moves by, that is behind this other flash, if you want to pick that one. Or at least behind anyone that is behind it as it moves this way. So we can see time dilation on here, we can see length contraction on here, we can see the relativity of simultaneity on here as well, which really shouldn't be that surprising because the whole thing is based on the Lorentz transformation, and out of which we get things like time dilation, length contraction, the relativity of simultaneity. So we spent a fair amount of time developing this tool, really, as it is, a visual tool for seeing some things about the implications of the special theory of relativity. Then we did another version of it where we didn't do two on the same plot, but we just said, okay, let's do a space-time diagram here. And let's note that when we put a light beam on the space-time diagram, if we can choose the units of c to be light years per year or light seconds per second, then c, the speed of light, has a value of 1. It's 1 light year per year or 1 light second per second, which is nice for us because if we use sort of regular units of time and distance like meters per second, then a light beam along here would be, very close to the x-axis, almost indistinguishable from the x-axis because it travels a very far distance in a very short amount of time. And so by choosing c equals 1 light year per year, 1 light second per second, 1 light day per day, 1 light month per month, whatever, then c becomes a world line on our diagram here that has a slope of 1. Or if it's going the opposite direction, a slope of -1, v equals minus c. And once again, you'll get tired of me saying this, but just as a reminder, this does not mean the light beam's going at an angle. Everything we're doing is going along the x-axis, just shows its progression in time. So time is flowing upward. In this case, it's moving along the x-axis at a velocity of c, which means it goes, maybe 1 light year here in 1 year of time, or 1 light day in 1 day of time, and so on and so forth. So we call this the light cone because as we analyzed it further, we said, if this is an event right here, or we're standing right here, can we influence events later in time? And we analyzed this and learned that as long as the event is within this cone here, this cone of light, then we can influence it because we can get a signal to that or actually travel to that space-time event in time to have some influence over it. Or down here, if we want to influence an event occurring here, anything in this cone here would work. But if we're outside the light cone, like say we're over here in this section, what that means is I'd have to travel faster than the speed of light to get there in the amount of time I have. The question we asked was, given the time I have, can I make that distance? Just like we often ask in real life if we're taking a trip. How long is it going to take? Do I have enough time to get there given the speed I can go? So here, the ultimate speed is the speed of light, and therefore we actually analyze it into 3 intervals based on our invariant interval to give some more insight into it. And we have the name time-like interval for really those things that occur in the cone here or the cone here. And what that meant, we didn't try to prove this, but we just stated it. It means that c squared t squared minus x squared, the value of the invariant interval between 2 points here, say the point here and then a point up here, if that's greater than 0, then it's possible to get there and have an influence on it. And what that means is ct is greater than x. If you think about it, c times t is the distance light can travel. If that's the ultimate speed limit, we can't go faster than that, then if the distance light can travel is greater than the distance we actually want to go, then yes, we can get there, in principle at least, assuming we can travel up to some speed less than the speed of light. So those would be locations in space and time that would be within the light cone here or here. A light-like interval then is when this equals 0 or ct equals x. In other words, the distance light can travel exactly equals the distance we need to go. And those are the values right on the light cone here. So if I'm here and there's a point out here, then I have a light-like interval between me. And if I can go at the speed of light, I can't go, but if I could shoot a laser beam, the laser beam could get there in time to get to that space-time point. If, however, the invariant interval between 2 points in space and time is less than 0, then that means ct is less than x. It means the distance is farther than a light beam could get there even. And therefore, I can't have any cause and effect relationship between them. And it'd be like, again, if I'm here, it'd be like I'm out over here or out over here. Or if I'm over here and I want to influence this point, I'd have to travel faster than the speed of light. And remember again that world lines with slopes less than 45 degrees on our diagram would indicate a speed faster than the speed of light. So we analyzed that a little bit. That was an interesting way to think about cause and effect relationships with this light cone diagram. And then we considered a couple of examples at the end where we had a question of, is faster than light travel possible? And we did it in a thought experiment, as it were, of a spaceship traveling from San Francisco to St. Louis to New York City and shooting off some flashes along the way. So the flashes, the images would continue on in front of them, go in front of them to an observer in New York City. And to the observer in New York City, it seemed like that they saw the image of the San Francisco photograph appear, and then the image of the St. Louis photograph appear pretty quickly after that, such that it seemed like the spaceship, went from San Francisco to St. Louis at maybe 4 times the speed of light, or even faster. And but clearly the ship was not going fast than the speed of light. It was just traveling. It's going very fast in our example, but clearly less than the speed of light. So it shows there can be situations where you can get observations that seem to show a violation of the fact that the speed of light is an ultimate speed limit, but when you analyze it further, it actually is not true. And then finally, we did an example with quote-unquote true faster than light travel. So we said, okay, what if we actually had a spaceship, where we could travel faster than the speed of light? What would be the implications of that? And we did a simple example with that, and the result was we saw a violation of cause and effect, that the effect of something actually did not happen after the cause, but happened before the cause. And the example we gave was an invention of a spaceship that could travel faster than light, and then catch up with another one and do a sneak attack on it. And what we showed in the frame of reference of the good guys who were being attacked, that the invention of the spaceship and their frame of reference actually happened after the sneak attack, which is clearly a violation of cause and effect. You can't have the sneak attack if the spaceship doesn't even exist yet. So it works backwards. Another way you could say it is that the spaceship actually attacked them first and then moved in their frame of reference back to its invention state. So it'd be like a little bit like time running backwards is one way to look at that. So anyway, true faster than light travel leads to true being it's not possible, but we do an example where we say, what if we could do it? Leads to violation of cause and effect. So next week, some of the things we've developed here will be useful. in thinking about things like the twin paradox, which we'll get to, and also things like the so-called pole in the barn paradox. And unlike this example of faster than light travel, which it's almost an optical illusion that you get that, these sort of strange paradoxes are actually true, and they come out of the special theory of relativity. So that's one of the things that we've been working toward, and we'll be getting to those next week.